Dr. Mummy is an assistant professor in the Department of Radiology at Duke University, and his research focuses on applications of xenon MRI in human lung disease, including asthma, chronic obstructive pulmonary disease, and interstitial lung diseases. He's especially interested in how biomarkers derived from ventilation and dissolved phase xenon imaging can be used to clinically aid diagnosis, prognosis, and therapy selection and monitoring. So with that, I'd like to hand the floor over to David. David, take it away.
All right, thanks, Brandon. Y'all can see my screen, right? Yes, perfect.
Yes.
And thanks, Peter and Lars, for organizing this event. I'm happy to be here. So my talk will be a little less technical because I am not a very technical person, but I want to talk about just generally our efforts as a site and as a field to move towards a sort of paradigm where we can share data and analyze the data in a common way for this xenon MRI to move towards the goal of clinical trials. Here's a quick outline. I'll do some introductions, both of my favorite topic myself and xenon MRI, a second favorite topic, and then talk about this clinical trials consortium we have going, talk about a multi-site clinical trial that we sort of did, further efforts at harmonization that kind of grew out of that effort, and some success stories, which is always good to end on, and then a few last thoughts that will stick with you for the rest of the next 10 minutes. So I won't recap all of this since Brandon hit the highlights, but I'm an assistant professor in the radiology department here at Duke. Since I have a BME PhD, being in the radiology department means I don't have to teach anything, which is great. This is my wife and I kayaking on a local lake here in North Carolina. And this is our dog in what could easily be a live look at right now because she does this a lot. So what is xenon MRI? We don't get beautiful pictures like Peter just showed you, but it's interesting in its own way. I'll give you just a real quick rundown. It's a hyperpolarization method like the hyperpolarized carbon Peter showed. So we have this gas blend that gets put in a hyperpolarized magnetic state and then dispensed into a bag, more or less in real time as needed. It can sit in the station for a few minutes and maintain its polarization. So it's not quite the rush of carbon-13. The subject is in the scanner, breathes in the dose from the bag, and then we can get a direct visualization of the gas as it distributes throughout the lungs. So this is an image of that what's called a ventilation image. This is contrasted with a really bare bones kind of proton MRI, but this is just to illustrate that unless you have fancy techniques, the lung is more or less a black box, but we can superpose our beautiful ventilation image and get a direct signal from the gas itself rather than trying to infer it. This is a completely fake image of a very interested radiologist looking at a montage, no doubt making a diagnosis. One of the strengths of this is that we can do an exam in a single breath hold, so it only takes about 15 seconds. You're only in the scanner for about 2 minutes per exam. And of course, being MRI, there's no ionizing radiation. But what is the secret sauce of xenon in particular is that when the gas is inhaled and into the alveolus here, it gets absorbed into the tissue and then into the red blood cells, and it undergoes a distinct frequency shift in the RBC, what's called the membrane, the tissue compartment, and in the air spaces. So we can actually decompose those through the magic of technical things and get separate color binned here images from the ventilation, membrane, and RBC compartments. So the thing to know here, much like Gordon Gekko in Wall Street, green is good. And if we're looking at a COPD image, you see these ventilation defects indicative of airway obstruction, RBC defects in the vasculature. And then in a fibrotic lung disease like IPF, we actually see an increased membrane signal, theoretically due to an inflammatory process or fibrosis. That's, again, just the one-on-one elevator pitch in a tall building crash course. And then just to highlight it, there's this other cool effect where if we look at that signal from the red blood cells specifically, it actually oscillates in tune with the cardiac cycle. So that's what we're looking at here, diastole and systole. And those oscillations themselves, affectionately dubbed the wiggles, are actually different in different diseases. And this can let us infer things about pulmonary hemodynamics. That's just for your interest and not really germane to understanding this talk. So like, this is all awesome, right? What's the problem? Why can't we just do this everywhere? Well, at the beginning, and to some extent today, we were just all speaking different languages, and we were suitably smoted. So pretty much everything can vary from site to site when you try to implement a relatively nascent technique like this. Polarization methods, the size of the bag varies, the way you coach the patient to breathe it in. Everyone has a different scanner platform and a different software version, and they implement their trajectories slightly differently or bigly differently. The reconstruction algorithms, analysis methods, output reporting and metrics, image and data storage, all these things can differ when people try to set this up from scratch. And that just makes it difficult to impossible to compare results from one site to another, except in a very kind of abstract, descriptive way. So thus enter an entity called the Xenon Clinical Trials Consortium to try to rebuild that Tower of Babel. And this was instituted in 2015 and is spearheaded by Jason Woods at Cincinnati Children's Hospital. And here's a map of the current sites involved in the consortium. There's about 15 active sites, and I think 2 or 3 more, this is a little out of date, who are getting stood up. And we get together every year to talk, and then we have periodic online meetings, and then a Slack group, which I love. This has been really helpful to help us kind of have a more formalized format for comparing our methods and driving towards some sort of harmony. The centerpiece of this is this manuscript that came out a few years back, spearheaded by Peter. And this has become just called the Consortium Protocol. And a bunch of the minds in the consortium got together and came up with standardized pull sequences and methods for doing kind of some basic bread and butter xenon imaging. So this was a really vital first step towards getting us all on the same page. And so we had some interest in from pharma in this, which was great. And so they came to us and wanted to set up a multi-site clinical trial in COPD with our newfound harmony. And this was Genentech, a study, and Tony Wong at Duke, Bastian at Duke, Mike Shim at UVA were some of the head honchos there. And then Laura Bell, who's now at GSK, Alexandra Coimbra. And there's no need to really look at this because we ended up not doing it. But things were, the study was pulled a lot early, not for scientific reasons. So we ended up doing 12 patients at 2 sites instead of our loftier goals, but it was still a really good road test of our ability to combine our data and put it together in a multi-site fashion. So I'm going to really focus on that harmonized protocol that grew from this study. We created an imaging manual. Laura was big in spearheading this, that we distributed to every site to do their imaging. And then Duke was both a site and also a central reader to do the analysis of the images. Here's us wearing our different hats to represent that. And so the way that would work was each site would send its raw data and DICOMs to the sponsor, Genentech. They would do basic QC involving like, are all the files there? They would send it to us, and we would return the analysis to Genentech. So, you know, when we were a site, we would send our data, they would send it back to us, and then we'd send it back to them, which seemed a little silly, but necessary. And so as our central reader, we would get the data sent to us, we would put it through our pipeline, create metrics, send it back to the sponsor, everything's peachy. We did run into just a few technical problems, as illustrated by these bullet points and these bullet points, and also these bullet points. So it was a lot more complicated than we expected, given that we put it all together in a really nice manual. In fact, we actually had to fail ourselves in our first quality control subject because we did not get it right. As a sidebar, I learned the first mention of the word facepalm was in 1996 on a Usenet group when I got this picture. I thought that was interesting. So there's a lot of growth opportunity here, as you can tell. And just to kind of distill those pages of notes, we had tried using the famous ISMRM MRD format to exchange data and found it. There were some areas where we needed to buff it out to be able to use Xenon data. We found that we had an ungodly amount of variables and assumptions baked into our software pipeline that didn't let us just plug and chug data from other sites due to our hubris. No matter how you specify it, trajectories come out just a little differently. People have different ways of reconstructing DICOMs. All of the things I kind of alluded to at that very beginning slide happened, and then some. So we did learn a lot from this, and I'm going to talk about those efforts coming up here. So we created a Xenon MRD format for exchanging data. We did a lot of improvements to our pipeline to make it more generalizable. We came up with a standardized quality assurance or quality control rubric to score incoming scans, which has proved really useful just outside this study. And then we wrote this all up in a white paper manuscript, which will hopefully be showing up soon. So I'm going to talk a little bit more now after I take a drink of water about those further efforts at harmonization. As I mentioned, we started with the ISMRM MRD format for exchanging data, and it needed to be expanded with some Xenon specific parameters. So we worked together with other consortium sites, and particularly want to shout out Andrew Hahn, Matt Wilmering, who was in the audience last I checked, and then Peter again, who we all worked together to come up with this spec. And also to generate platform-specific converters to take your data off your scanner and put it into the MRD format. Of course, that has to be different for each scanner platform. And so we've got that spec, and then also all those different converters available on our Xenon Consortium GitHub. The spec has been so handy because now when we get data and it's not per spec, we can point to it and say, you're not per spec, go fix this, which is a lot better than saying, oh, well, we kind of wanted it this way, but maybe we can change it for you, and which is kind of how we started. And so there's a little bit of like, give and take as you put it together. But then once people sign off on it, it's a really nice kind of independent judge. We also put all of our Duke pipelines on GitHub. These are the ones that we've used for our production data and in this study and in future clinical studies. They show as private here just because I didn't update the screenshot, but they are now actually public. So you can do, I didn't talk about all these different scans, but there's multiple flavors of Xenon scan, and you can go in and grab those pipelines and run it to your heart's content. We encourage all of our users to flag bugs and raise future requests. We've had kind of the same, well, I won't necessarily say issue because this is so young, but we're taking steps, as Peter talked about, to add engagement. And we actually have our first power user, Yoni Friedlander at McMaster, who raised his own issue and suggested a fix and pushed it, and we reviewed it and merged it. And that was like one small step for a coder, but one giant leap for our open source paradigm. So that's been really good to see, and we're hoping for more of that too. And these just a shout out to our students, current and past, who've particularly helped spearhead this effort. And then I mentioned these quality control checks. So it's really hard, we found, to do this objectively, other than some things like SNR that you can quantitatively score. So we ended up coming up with this rubric ranging from 1 being uninterpretable to 5 being excellent, and then the Likert score in between. And this actually, like, once you do a few of these, your gut tells you pretty quickly, your own neural network, I guess, what that score should be. So we did find this pretty helpful and that we were pretty consistent. So I can give a few quick examples here. So just to get you the lay of the land, this is a typical montage from a ventilation scan, like I showed at the beginning. And we're going anterior to posterior. So this isn't time or anything. This is just the Z, or well, whatever you want to think of it. This is just that axis of AP axis. And then this is the corresponding proton scan. And then these are our color binned images where green is good. And this is great. Like, this is perfect. If we had one of these for every scan, we could retire rich and famous. Here's one that's pretty good, but you can see they left some field of view on the table. So we could have maybe made our slices a little bit thinner and picked up more detail rather than just wasting these slices. So they got dinged a little bit. It's not an artifact, but could have been a little better. And then here's one where, see if you can spot the difference. There was clearly some kind of RF interference or something in this one slice. And so this got dinged down to a 3. Moderate artifacts, mild decrease in confidence, but the rest of it is fine. And then going into gas exchange, so I'll reorient you. Now we have those 3 compartments that I talked about at the beginning: the ventilation, the membrane signal, and the RBC signal. And looking at this one, this is great. A little bit of noise in the RBC signal is normal because like by the time the gas gets that far, the signal is just naturally pretty low. So this is a Mary Poppins, practically perfect in every way. And then here we see a little bit of noise creeping in. The RBC is getting a little dodgy, but for an RBC signal, that's not too bad. And then here we've got a lot of noise. This one's okay. I guess this is all right. And this is just a dumpster fire. So this one got down to a 2. And the kind of rubric that or the threshold that we landed on was that a 3 or above would be usable in a data set, and anything under that would not be. And we actually were able to diagnose by tracking these that one of our sites had a bad TR switch because their SNR was slowly degrading over time. So we were able to flag that as the study went on. They fixed it and everything got better. So we've really adhered to this as a general mindset outside of that study. So we've grown those tools and they've kind of taken on a life of their own outside that initial clinical study, which is great. So I want to just talk about a few success stories that sprang from that, and then leave you with words of wisdom. So this is the piece de resistance of that original Genentech study. Now, we only actually used 2 of the sites, got as far as recruiting patients before the rug got pulled out from under us, but we did do qualifying scans on quite a few sites. Duke, Kansas, Missouri, Virginia, Iowa, McMaster, Sheffield, and Cincinnati on all 3 scanner platforms. And after all that back and forth and all those bullet points and refining our methods and everything, we got to a point where we were able to process all of their gas exchange data on healthy subjects, and they looked like healthy subjects. So this isn't a clinically meaningful result in its own right, but as far as a springboard, we were really excited about this and just that ability to kind of get us all into a single playing field. This is tear-jerkingly beautiful if you spent years on this. A grad student in our lab, Supachart Liwiwang, has been working on describing what a pristine healthy reference, and this is a distribution of image intensities, and what that looks like across multiple sites on different platforms. So going back, I didn't really explain this because of time, but these bins are all based on a known healthy reference cohort of young, healthy, disease-free subjects. And so he's working to gather the data from across all these 3 sites and platforms and put them all together and show that we can make a usable reference that way, so we're not weighted towards one site. We had a collaboration with Rachel Eddy at UBC and Peter, where we got 135 subjects together and did a cluster analysis with long haul COVID. And this is like way more subjects than we would ever have been able to recruit for this cohort at Duke. And with our powers combined, it just gave us the ability to do this sort of thing, which is just really rewarding. And then a grad student of mine here, Andrew McHorse, is working on, well, coincidentally, almost the same size, but this population is on all healthy subjects. And these are metrics I didn't talk about from the spectroscopy specifically. But the main takeaway here is we're doing these curve fits to measure the effects of age and then behind the scenes sex and BMI. And we just wouldn't be able to hang our hat on these results with the subjects we'd be able to recruit at any individual site. But because we have this framework, we can throw them all together, which in a relatively painless process, I would say this time around. Peter might disagree, but I think it was pretty smooth. And it's just a new world for this sort of study. And so not to be too grandiose, but here are my final thoughts that have been really set in stone after I made them up over lunch a few hours ago. So some basic principles. It's harder than you think. Like things will go wrong in ways you never anticipated and you'll need to deal with them, but it does get easier every time. So build that in. Write everything down that you do, that you have to fix, every site specific thing, you'll forget it. Communicate with those sites. Don't assume they are on the same page with you and vice versa, because there's all these unspoken things that come to light when you're trying to do this sort of collaboration. No battle plan survives contact with collaborators, so iterate. We got into this thing where when for our qualifying scans specifically, some of the sites kind of thought of it as this exam they had to pass. So they would like go off and do it all on their own and then send us the scans and like wait, in trepidation. And it would have been a lot easier, we realized, if we'd done iterative, like just, send us your DICOMs and we can go back to you and let's have a Q&A and all of this stuff. So like, don't treat it like an exam. It's an iterative thing you're building together. And if you do build it and it's a decent product, they will come and they'll make it stronger as a result, as we've seen from all the interaction with our groups, and then with Yoni Friedlander specifically, starting to push code changes, and it's all worth it, because as all the reasons Peter said, it's selfishly worth it to get visibility and to have other people using your methods so that you don't have to adhere to other people's standards, and it's just good for the field. Like these things are really really beneficial, especially as we get new sites coming online. We can go to them with like, here's a package of the software you need and the know-how you need. Let's just help you. You don't have to reinvent the wheel here. So with that, I will show my acknowledgement slides. One specific collaborator I want to shout out specifically down in the corner there. And thanks again for having me here, and I'm happy to take questions.